This video will look at the relationships between Ka and pKa and Kb and pKb. We will also look at the connection between the Ka of a conjugate acid and the Kb of its conjugate base, which are related through the autoionization of water. A weak acid undergoes equilibrium to dissociate into H+ and its conjugate base, which we're writing as A-. We can write a mass action expression for this equilibrium following our usual rules. Instead of Kc, we call the equilibrium constant Ka, which stands for acid dissociation constant. We can also apply the mathematical operation P of x equals negative log of x and convert between Ka and pKa as needed. For a weak base, the equilibrium shows its reaction with water to produce the conjugate acid Ha and hydroxide ion. The mass action expression for Kb and the conversion between Kb and pKb are set up similarly as that for the weak acid. We'll see in some of our problem solving that there will be times, for example, when we'll be given the Ka for an acid, but we need the Kb of the conjugate base. They are connected through the equation Ka times Kb equals Kw. The equation can be rearranged to solve for Ka or Kb depending on the information provided. The pKa and pKb values are also related in a similar way as pH and pOH, where pKa plus pKb equals 14.00. Converting between pKb and pKa comes up quite a bit during buffer calculations, but we'll also see it when working on problems involving salt solutions. And just like the other situations where we're using Kw or pKw, these values are not exact. Kw has 2 sig figs at 25 degrees Celsius, and pKw has 2 decimal places. In our first example, we're given the Ka for hypochlorous acid, and we need to calculate the pKa. So the equation we're using is pKa equals negative log of Ka. So all we do is plug in the value of Ka. So we have pKa equals negative log of 2.9 times 10 to the negative 8. Our calculation is a log, and so we have our 2 sig figs in the value, and we'll report 2 decimal places in the calculated result. So doing the math, negative log of 2.9 times 10 to the negative 8, rounded to 2 decimal places, gives us 7.54. Our next example is going in the other direction. We're given the pKa and we need to calculate Ka for acetic acid. So we'll start with the same equation, pKa equals negative log of Ka, and we'll rearrange it to solve for Ka. If we multiply each side by -1, that will give us negative pKa equals positive log of Ka. Then, if we take the antilog of each side, we'll end up with 10 to the negative pKa equals Ka. Because if we take the antilog of a log, they basically cancel each other out. So our equation is Ka equals 10 to the negative pKa. So plugging in our values, we have 10 to the negative 4.74. Our sig figs are going to go in reverse compared to the previous problem. So we have 2 decimal places in our pKa, and that is going to end up giving us 2 sig figs in our calculation. So doing the math, make sure you use your antilog key for this. We have 10 to the negative 4.74, and that gives us to 2 sig figs 1.8 times 10 to the negative 5. Our next example is now relating Kb and pKb. We need to calculate the pKb, so our equation is similar to that for Ka. We have pKb equals negative log of Kb, so we can just plug in the information we're given. So we have negative log of 1.7 times 10 to the negative 5. Our sig figs will go from 2 sig figs to 2 decimal places. And then doing the math, we end up with 4.77 for our pKb. And then a similar example as we had for Ka going in the other direction, we're given the pKb for dimethylamine, and we want to calculate the Kb. So pKb equals negative log of Kb. Take the negative of each side, and then take the antilog of each side. So you can see that the equations are similar. In fact, they're almost identical. We end up with Kb equals 10 to the negative pKb. So plugging in our value, we have 10 to the negative 3.23. Our 2 decimal places will become 2 sig figs after we do the calculation. And 10 to the negative 3.23 rounded to 2 sig figs gives us 5.9 times 10 to the negative 4 for Kb. In this example, we're given a Ka for a weak acid, benzoic acid, and we're asked to calculate Kb for the conjugate base. So our Ka equals 6.3 times 10 to the negative 5. The equation we use to relate the two is Ka times Kb equals K water, which at 25 degrees is 1.0 times 10 to the negative 14. We'll rearrange this equation to solve for Kb. So if we divide both sides by Ka, then we get Kb equals 1.0 times 10 to the negative 14 divided by Ka. So plugging in our Ka, Kb equals 1.0 times 10 to the negative 14 divided by 6.3 times 10 to the negative 5. Both of our values have 2 sig figs, so our Kb will also have 2 sig figs. So doing the math, 1.0 times 10 to the negative 14 divided by 6.3 times 10 to the negative 5, rounded to 2 sig figs gives us 1.6 times 10 to the negative 10. It's worth repeating that a Ka must apply to a substance acting as an acid, as a weak acid, and Kb must apply to a substance acting as a weak base. So we cannot have a Kb for benzoic acid. The Kb is for the conjugate base benzoate. And in our final example, we're given a pKb for a weak base, and we want to calculate the pKa for its conjugate acid. Here, we can use the relationship pKa plus pKb equals 14.00. So rearranging to solve for pKa, we get pKa equals 14.00 minus pKb. Our sig figs are going to be following the rules of addition and subtraction, and so we are going to be looking at the number of decimal places. So plugging in our values, we have pKa equals 14.00 minus 4.76. Both values have 2 decimal places, so our final result will be rounded to 2 decimal places as well. Doing the math, 14.00 minus 4.76 gives us 9.24 for our pKa. I'll make a similar comment as I did in the previous example. A pKb must apply to a weak base, and a pKa must apply to a weak acid. So again, we're asked to calculate pKa. It's not the pKa of ammonia, it's the pKa of its conjugate acid, which is ammonium ion.